in the previous video what we had actually discussed was Strauger based exchanges, and I talked about basic components like two motion selector and uniselector, which are basic stuff by which Strauger switches are built. But remember, those were mechanical systems, and normally once they are mechanical there will be a lot of wear and tear in them. You need to repair them very frequently, and of course they can actually get faulty at the time when you do not need them to be faulty. So, reliability is poor, and normally these kind of systems will have, size was actually pretty large, and there was another thing that we were using a pulsing mechanism. So, if I want to dial number 9, I have to send 9 pulses, which will then lead to the setting up of these uniselector switches or two motion selector switches when two actually set of pulses were sent. So, the time was pretty large. So, people were actually already thinking to make it something which is going to be easier to maintain and less wear and tear will be there. So, people came up with the idea of something known as crossbar switches. So, essentially what we are trying is, we are trying to set up a path. So, I need only a switch, and these switches, if they are actually in open air, will lead to oxidation problem, there will be sparks and all that thing. So, the way it happened is, we actually have been using incandescent lamps which were actually sealed in glass bulb, and when this tungsten filament actually gets heated up, it does not get oxidized because I am actually going to put in inert gas inside. All I am also actually going to do is I am going to use it at lower pressure. So, the oxidation problem will not be there. I think same idea was taken, that if I can actually encapsulate this switch, mechanical switch, inside a glass bulb, so oxidation will be much less. So, this switch can actually make a very good contact. This contact can be made very good for very long duration, for number of snaps for which this switch can be operated will be much larger, and that what actually led to something known as cross point. Okay. So, this basic element of cross point now can actually be used to build a crossbar switch, and of course, this also leads to something known as cross point complexity estimation in the switches. So, we will be actually, let us look at this, how this switch is going to be built. So, mostly there will be cross point will contain two arms, that was the basic structure, and these are the two switching points. So, one point is being connected here, the other path is connected here, and whenever these two will actually move down, so this move downward, this moves upward, so they will make a contact like this, and then the connection is there between the two arms. But how this movement will actually happen? So, for this, and of course, now what we have to also do is, we have to take care of this movement, we have to also encapsulate this thing in a glass bulb, so that the dust particle will not actually interfere with the performance, which was the problem with the mechanical system of Strauger. This also is an electromechanical system. So, we will normally encapsulate into a glass bulb. We can remove the oxygen from inside and we can put the inert gas, or we can put anything which will avoid the oxidation of these cross points, and they can operate for longer number of operations. Now, for creating motion, I can actually create, these are magnetic paths. So, and then I can actually have electromagnet, so which can be controlled by applying a voltage here. Similarly, I can actually have the second electromagnet, and this is the second control point, this is V1 and V2, when both of them are being activated. So, in order to minimize the reluctance of this particular path, it will pull up this particular arm upward, this electromagnet will pull this arm downward and the connection will snap in. So, technically there is an input, there is an output and there are two control points. When both of them are in excited state, you will actually get a snapped connection which will work, okay, which will lead to the setting up of the connection. This was the basic thing. Now, how to build up a switch with this? So, important thing is that I need not send the pulses, I can send even DTMF or multi-frequency key pulsing kind of phenomena, whereby a number I can actually define various frequencies, the two set of frequencies which are there. So, when I do set these two frequencies, I am sending number 0, when I do this and this, I am sending number 2. So, depending on which pair has been sent, I can determine what is the number, and that actually can be used to snap different cross points. I did not do this giving key pulses which will lead to what we call movement of the arm of a Strauger. So, that kind of phenomena is not required. So, this is what is the basic element. So, the basic structure of a cross point will look something like this, a crossbar will look something like this. So, this is the output arms, I can connect the input arms also here. So, I am connecting 1, 2, 3 and 4 to 1 prime, 2 prime, 3 prime and 4 prime, and these wires where actually we will put the cross point. So, this will look something like this. So, whenever the cross point will snap, the connection will happen and 1 prime can get connected to 3 prime. This is the point in 1 3 prime. So, this is what it looks like. And of course, you will also have the electromagnets. So, this is the what we call a column control and this is a row control. So, when both of these are excited, the connection will snap and 1 will be get connected to 3 prime. Okay. So, that is what basically is how this cross point is being used at each one of these point where the two lines are crossing or two buses are crossing. So, in total number of cross points which will be required in this case will be 16, 4 is square, 4 into 4. Okay. So, in general for a n cross n switch, I require number of cross points which will be equal to n square. So, complexity of the cross points will be O n square, and of course, there has to be logic whenever you dial a number, this number has to be trapped here, based on that some analysis has to be done, and then a logic will activate the cross points which will cause the setting up of the connection. Okay. So, we will do this particular basic controls of a switch maybe in another video. So, this mechanism is what is known as crossbar. So, I need to set up cross points for setting up a connection from the input side to the output side. Normally these are unidirectional or these can also be bidirectional. Okay. So, if it is analog communication, this can becomes analog switch, if it is a digital signals being transported, it becomes a digital switch. Okay. But it has capability of doing both. So, if you want to set up a communication between node 1 and node 2, so node 1 is connected to 1, so this means a communication path has to be set up in both the directions. So, which actually implies that from node 1 I will set up a path to 2 prime, so which is going to node 2, this is the node, this is also coming from node 2, remember. So, I need to set up this and I need to set up 2 to 1. So, I need to snap this as well as this. So, these two has to be snapped for setting up a connection between 1 and 2. because we always set up a bidirectional connection. Okay. And normally the structure, because I am taking this switch as a unidirectional system, these are the input, these are the outputs, I need to use something called duplexer, because when I am connecting to node 1, I am actually connecting these 2 wires to the node 1, and normally there is only one wire pair which is going to the node, so on which the transmit and receive both will be happening. So we will be actually connecting something known as duplexer. So duplexer only splits incoming and outgoing signal. So this is a signal going into the switch, this is coming from the switch, and this is a bidirectional. So same thing will be happening for node 2, and I can do the same thing for node 3, this for node 4. So I will have a bidirectional links going to the switch, and this is basically how the switch will look like. So input and output are actually paired ports which belong to the same node. So setting up a communication from 1 to 1 prime actually does not make any sense, because they are both connected to the same node. Okay. So this particular unit is what is known as duplexer. In digital systems, of course, we do not have a duplexer kind of thing, this is for analog telephony. So analog signals which are coming in this direction, analog signals which are going in this direction. These are basically 2 voltage waveforms going voltage waves which are moving in opposite directions. Now if inside of this switch these are not unidirectional, because those will be required if it is a digital signal, but if it is analog signal I need not, because what I need to do is I need to make a connection between this wire and this wire for a communication to happen. So if there is everything is bidirectional, in that case number of required cross points will be less. So let us see how actually it will happen. So in a bidirectional system, so one wants to connect. So these are actually meaningless in a sense, because this can communicate in both ways. One is not going to talk to one, but if one wants to talk to 2, so 2 is this line. So these are only points which are going to be used so that the communication can happen between 1 and 2. So I can snap in these 2 if between a connection has to happen between 1 and 2. Okay. If connection has to happen between now 1 and 2, I cannot use this wire, remember, I have to use some other wire. Okay. So in that case, if I want to make a connection between 1 and 3, I may not choose this, I may choose these 2 snaps. So the routing between 1 and 3 is happening here. If I want to do 1 and 4, I have to do the snap on this particular thing. So one can get connected to any one of these actually. But what about 2? If 2 wants to get connected to 1, this route is already available, only I need to bother about that 2 can connect to 3 and 4. Even if 1 is connected to any one of these things, so I can actually have cross points which are available. So 2 can connect to 3 and 4 via this route. So 1 it can always connect through this. So 1 is connected to anybody, but 2 can still connect. So I am actually creating a special configuration whereby any earlier connection need not be dismantled for a new connection. So if 1 and for example 3, 1 and 4 are being connected via this route, so I can use the next one to connect to 3. So this 2 actually can be used in that case. Okay. So then I will be requiring only these many, that is what we will actually think. Actually you do not need these ones. If I actually short these lines with these input lines, if I connect this one here, permanent, there is a permanent connection between 1 and 1, 2 and 2, 3 and 3 and 4 and 4. So, this is already connected to 4, this is already connected to 3, the second one is already connected to 2, one is connected to 1. So, these are straight lines. So, I only require cross points at these points. Okay. That is it, and that is good enough for setting up of the connection anywhere. Okay. So, 3, 4, I need only bottom half or I need only the upper half, diagonal half for making up the connection. So, number of cross points which will be required in this scenario will be n into n minus 1 by 2, NC2 combinations which will be required. If I even use these particular cross points, in that case I will be requiring, if I am counting even these, which of course is not required if this permanent shorting is not there, then I require n into n plus 1 by 2. But both ways you can actually see my complexity is growing with O(n) square. So, this actually implies as my n number of nodes are growing, number of cross points required actually grows proportionally to the n square, or it always remains what is, it is being upper bounded by n square actually. So, which is what is a cross points characteristic. Ideally I would like to have, if the number of users are growing, it should be linear if it is possible. So, you will be looking into this what actually best we can get. So, either I will get this, I will get this if I use even these cross points I will count, in that case this one. If I do not count these diagonal ones, only the bottom half or the only upper half, this is the one. If I have the complete crossbar, when all cross points are being used, this unidirectional configuration which I was talking about, I require n square in that case. So, in all the cases O(n) square will be the complexity. Now, there is one very important property which I would like to now put in, explain. This is known as strictly non-blocking property, which is being maintained by this switch. Okay. In this switch, if an input is there, if an input is free, there are two conditions, an output is free and I want to connect these, I want to connect these two. I can always do it without disturbing the existing connections. And that is what we known as, what we call as strictly non-blocking property. So, if I want to compare any other switch design, it should also be strictly non-blocking, then only I should compare the complexity of crossbar with that particular switch. Now, question is how I am going to do the control. I have already explained there will be two control points which are required, both of them need to be excited together so that a connection can snap. Okay. So, what I can do is I can join these R and C together and there is only one control point. So, I require 16 control points for a 4 by 4 switch. In general, for n by n switch, I will be requiring n square control wires. So, depending on which particular cross point has to be activated, I will activate one of these lines. So, different pairs will be combined at different point of time. In this case, how many cross points will actually be required? One cross point consumes one pair of nodes. So, technically n by 2 cross points will be required at any point of time, remaining will not be used. So, you will have n by 2 divided by n square, that will be the cross point utilization. So, I am going to use too many cross points, but all of them will not be used all the time for making up the connection. So, maximum utilization for a cross point will be n by 2 divided by n square, which is 1 over 2n. So, as switch size actually grows, the switch utilization, the cross point utilization will go to 0. This is something which is actually not good, and of course, a cross point utilization will go to 0, that I can't control because I have to have those many cross points. But my control wires, I am going to have n square control wires, this is also utilization of the control wires. Can I take care of this? Okay. So, can I actually make, because I require only n by 2 cross points to be activated. So, I can probably work with less number of control wires. I require in general a linearly scalable number of control wires. So, one option is that we define a common control line which will control all the column controls of these cross points, and we will do it for the complete switch, and similarly we will do it for the row, and let us see how we can build up a control line. So, we have again this 4 by 4 crossbar. So, I will take a red colored chalk and use it for drawing the control lines. So, I will have a control line for this. So, this is actually now exciting that electrode which was there, electromagnet. So, this one is the column, this one will be the row. So, I am actually drawing this red colored, this is a control line, I call it C1, C2, C3, C4, there are 4 control lines, and similarly I can actually have a row control lines, column control lines, sorry these should be row actually. So, the column control lines will be these. So, whenever I want to snap a cross point, for example this one, I need to now activate R1 and C3, and then this cross point will get activated and a connection will be set up between 1 and 3 prime. Okay. So, of course, we can actually tweak with this thing and do it for this kind of configuration of crossbars also. Okay. But let us take it in general sense here, the same thing now can be evolved even for the other kind of stuff. So, is it going to create a problem or is it okay? So, we need to ask this question. So, let us try to set up 2 different kind of connections and see if this can work out. So, let me see if I want to set up a connection, say 1 to 2 prime and 2 to 3 prime, that is a connection which I want. Okay. I am not talking about a bidirectional thing, I am talking about unidirectional connection. So, for me 1 to 2 prime and 2 to 1 prime are 2 different connections. Normally they will be done in pairs for voice communication. For data communication they can be done one by one at a time. So, if I want to set up these connections, my common sense says that I need to have, depending on the which particular row I am going to activate, I will choose that row and I will choose a corresponding column. So, I want to go from row 1 to column 2. So, I should activate here row 1 and column 2, and this will cause 1 2 prime. So, this particular connection will get snapped. Okay. So, let me remove this because I need, and for this one I will say I will do R2 and C3. Fine, you do R2 and C3 and this connection will snap in. But R1 C2 is fine, R2 C3 is fine, but there is a R2 C2 and R1 C3, this is also combination is possible when you are activating these lines, which actually means R1 C3, R1 C3 means this particular connection, and R2 and C2 means this particular connection will also get snapped in. I never wanted, this is undesirable, this is undesirable, this is also getting snapped. So, this scheme is not going to work, though my number of control lines here are now 2n, which will give me a complexity of a linear complexity. So, I have to use some technique. So, maybe one idea is that if we do it in an order, say I do row first and then column, then only the connection can snap in. If I do column first and row later, it will not. So, if we do that, so I do this thing first and then I do this one. So, now what are the valid combinations which can form? So, I did R1 C2, so this connection snaps, then I did R2 C3, this connection snap, but I also did R1 and C3. This also is a valid combination because sequence is retained. For this, sequence is not as per our requirement. So, if I put a logic here that in this sequence the activation should happen, I will set up 1 2 prime, 2 3 prime, and I will set up 1 3 prime also. So, this will be happening and this I will be able to block. So, I am successful at least partially now, but this undesirable thing is also happening. What to do with this? So, this scheme of maintaining a sequence that row first and column second will also not work. So, we have to now innovate further. So, what we can do is, and of course, we can also see that here we have to now carefully observe that it is possible that one input can connect to multiple outputs. This is a valid combination, we call it a multicast. We call this kind of configuration as a multicast configuration. When you have only one input and you have only one output to be connected, this is known as unicast connection. When one input is connected to all the outputs, it is known as broadcast connection. Okay. So, since these switches can also operate as multicast and broadcast switches, I need to look into this actually. Then this is a broadcast. So, we can actually see that one input can connect to multiple of these outputs, but is it possible that one output can connect to more than one input? This is not possible. I am not going to mix the inputs coming from multiple outputs and put them into one output, that is never going to happen. So, I think for holding on to the connections, so which one of these lines have to be done? My control lines are good enough to hold on to the connection, I do not need row line to be activated. So, I can now use a sequence, a time sequence to encode which particular cross points need to be activated. So, the logic which actually can be used, which the clue comes from here, is that I will activate the row first, I will activate the column. The moment this is done, my connection will snap or connection will be made, and if I now put down my row, the connection will still remain on, it will not go off, and now this, whenever your column goes down, then the connection closes. Connection will go till this particular time, connection is free. So, I can use this encoding and this works beautifully. So, let us see how it will work in this case, and then we will do an example. So, for this particular case, let us see how it is going to happen. I will set up this one. So, I will set up R1, I will set up C2, the connection will snap. So, 1 to 2 prime connection is on here, okay, this will start, and then R1 goes down, connection will remain, and then after some time you will have R2 goes up, this connection will remain, C3 will go up, at this point 2 to 3 prime will get activated. Remember, there is only C2 which is activated here, and R2 has R2 C2, the problem which was happening, there is R1 C3. So, R1 is down, it is no more up. So, when C3 goes up, R1 has not gone up first. So, 1 3 which was happening here, this also has been taken care of. So, 1 3 cannot snap in, and yeah, 2 2 will also not snap in, R2 C2, because the connection order actually has been changed. So, and then of course, you put down R2, both the connections will keep on going. When you will put down your C2 will go down, this will be closed. Whenever your C3 goes down, this connection will be closed, no confusion. For holding on to the connection, I only need C2 and C3, that is what I was telling, only these control lines which are required. So, I can actually use only 2 n control lines and row and column, and only just for holding on to the connection n control lines are good enough, because there will be n outputs which can be busy. And if, for example, now you will ask that how I am going to implement a multicast. So, if you want to have a connection where 1 is going to communicate to 2 prime, 1 prime and 4 prime, is going to be simple. You will put R1 up, then you will put C1 C2 up, you will put C1 up, and you will put C4 up. You will find that 1 2, 1 1 and 1 4 connections will snap in. So, at this point 1 2, at this point 1 1, and at this point 1 4 will snap in, and then you can put R1 down, they will remain as it is till the time the corresponding control lines are maintained up. The moment you actually put C2 down, 1 2 prime will go, the moment you put C1 down, this will close, and whenever you put C4 down, the last one will go. That is how you will implement a multicast configuration. And of course, now you should ask that how I am going to implement this logic, this particular sequence mechanism. So, what I need to do is, I am not going to use simply these electromagnets, I will actually use a logic here, and it is not a simply a combinatorial logic, it is going to also be dependent on the state, the earlier state. So, it is going to be a sequential logic which have to be built. So, whether the switch was in on state or off state and what is my current input, that will decide what is going to be my next state. So, that logic actually can be used to do the computation, okay, and build up a logic which will operate on this particular switch. So, I am just going to give you the logic table and then I will discuss this logic in the next video. As a solution to the assignment, this basically becomes an assignment first for you, that how this logic is built. So, you do the logic thing after looking at my state table diagram, and the logic we will discuss later on, or maybe this can be given as a solution to the assignment. So, you have R and C which are coming, there is a logic which will maintain the state, and this is the control line which actually goes to both the electromagnets of the crossbar cross point. So, this logic has to maintain the state. So, you have to essentially, once you get the table, you have to then use a logic to build up a sequential diagram, sequential logic gate. So, you have to maintain what is the previous state, okay, what is the input R and C, and what is going to be the next state. Only this need to be identified, okay. So, you can be either in on state or off state. So, if you are in on state, you will have only 4 possibilities, and you are in off state, you will have again the 4 possibilities. Let us see what is going to happen with this. We will decide the next state based on that. So, if you are in the on state, both R and C goes to 0, next state obviously should be off, the connection should be unsnapped or should be released. On means the connection is snapped or connection is maintained. If connection is in the on state, control line remains up, this is immaterial actually whether it is 0 or 1, in both cases it should remain on. Okay. If it is in on state, my control line goes to 0 irrespective of whether rho is high or low, does not matter, this should go to the off state. Okay. So, normally in my operation this issue has not come, because I have not put my column down before the row has gone, row has always gone down first. It was R1, C1, both are going up and then R1 going down, but this actually means a different scenario, but logic circuit has to take care of all kind of situations. So, when it is in off state, both are 0, it remains in off. When it is in off state, it cannot go to on state actually, okay, because only column has gone first. So, this has to be off. When it is off, row has gone up, this actually means you are in, I have to also maintain a third state actually here, because I have to maintain that row actually has gone first. So, I will call it on, off and intermediate state. So, let me put it that way. So, if it is on, this remains, this goes to off, this remains to on, this goes to off, the column has gone down. In fact, this goes to the intermediate state. Okay. If it is on, I cannot go, if this both actually cannot, both simultaneously, this remains on, right. This normally will not happen, you have to always go to an intermediate state, okay, because from intermediate you can come to this. So, you will have an intermediate and then there is an on state, yeah, it will remain on. If it is off, it will remain off, this is off, it remains off, this goes to intermediate state. It is off if both by chance goes to 1. This actually is not possible because you have to be in the intermediate state before you come here. Okay. This is possible because from intermediate you can go to on state by having 1 1. Okay. And then if there is a 1 1 is being maintained, you will remain in on, but this cannot happen. Okay. So, but technically if this is somehow happens simultaneously, this should remain in off state, this cannot go to on. Okay, because C might have gone become 1 first and then R might have become second, then this will remain in off. So, other way around you always go to first to the intermediate state, and then of course the third option is intermediate state, which I can write here. Based on this logic, based on this table, actually you can build up a switch. So, previous state is I should put R and C, the next state. So, if it is 0 0, so you are in intermediate state means the R has gone up, and if it goes to 0 0, next state will be 0 off. Okay. So, you were in this state 1 0, you cannot actually move from 1 0 to 0 1. So, both again is flipping simultaneously. So, this is an invalid thing. So, from 0 0 you have to go to 1 0 and then to 1 1. Okay. So, you cannot go from 0 1 to 1 0 to 0 1. So, normally this will not happen, but if this happens simultaneously, this should be off. Okay. But this actually in implementation will never happen. This you are in intermediate state, you will remain in intermediate state, and if you are in intermediate state both goes 1, you will become on in that case. So, that builds up the complete logic, and I can actually build up a state diagram for this. So, this will become more clear. So, that is what the logic which has to be built here, and this will become the full cross point module which will be used in the crossbar switch. So, you can actually you will be in either off state. So, you can apply from here, you can figure out that if you are 0 0 you will remain there, if you are actually 0 1 you remain there off, if you are actually going to have 1 0 then you go to the intermediate state from where you can go to on, and if there is 1 1, remember both the inputs cannot go simultaneously from 0 0 to 1 1. So, but 0 0 if it can goes to 0 1 it remains in off state, then it goes to 1, then it will remain there itself. Okay. So, you have to go through 1 0 sequence first to go to intermediate. So, you can actually go from 0 0, you remain in off, then you apply 0 1, you remain in off, then this one actually has gone 1, the next one this goes to 1. So, you are now applying 1 1, you remain in off because of that. So, when you are in I state, you can actually apply 0 0, you will go back here, you apply 0 1, okay, which both the digits which are getting flipped simultaneously, which is not possible. You cannot go from 1 0 to 0 1 at the inputs. So, they actually one of them has to flip. So, 1 0 only one bit will be changing at any point of time, but this actually means it has to go to off if it happens. So, and if it is 1 1 then it will go to on state. Okay. And in on state if it is 0 0, and if it is 0 1, so basically R has gone down, that is what it means. So it remains in the on state, and if it goes to 1 0 somehow, from 0 1 if you flip to 1 0, then it will go to intermediate state, or if you go from 1 1 to 1 0, then also it comes to the intermediate state. Okay. And of course, then if it remains 1 1, it will remain in on state. So that what becomes your state diagram, which has to be used to build up the logic to control the cross point. So next video we will try to see that number cross point complexity is O n square. Now question is, if I want to build up larger and larger dimensional switches, what problems I am going to face? We will look into that, and we will see how we will go logically to the multi-stage interconnection networks.